In a sphere, a bonded electron transfer is a redox chemical reaction that proceeds via a covalent linkage, a strong electronic interaction between the oxidant and the reductant reactants. In a sphere, is electron transfer, e.t. A ligand bridges the two metal redox centers during the electron transfer event. In a sphere, reactions are inhibited by large ligands, which prevent the formation of the crucial bridged intermediate. Thus, ET is rare in biological systems, where redox sites are often shielded by bulky proteins. In a sphere, ET is usually used to describe reactions involving transition metal complexes, and most of this article is written from this perspective. However, redox centers can consist of organic groups rather than metal centers. The bridging ligand could be virtually any entity that can convey electrons. Typically, such a ligand has more than one lone electron pair, such that it can serve as an electron donor to both the reductant and the oxidant. Common bridging ligands include the halides and the pseudohalides such as hydroxide and thiocyanate. More complex bridging ligands are also well known, including oxalate, malonate, and pyrazine. Prior to ET, the bridged complex must form, and such processes are often highly reversible. Electron transfer occurs through the bridge once it is established. In some cases, the stable bridged structure may exist in the ground state. In other cases, the bridged structure may be a transiently formed intermediate, or else as a transition state during the reaction. The alternative to inner sphere electron transfer is outer sphere electron transfer. In any transition metal redox process, the mechanism can be assumed to be outer sphere unless the conditions of the inner sphere are met. Inner sphere electron transfer is generally enthalpically more favorable than outer sphere electron transfer due to a larger degree of interaction between the metal centers involved. However, inner sphere electron transfer is usually entropically less favorable since the two sites involved must become more ordered, come together via a bridge, than in outer sphere electron transfer. Tauber's experiment. The discoverer of the inner sphere mechanism was Henry Tauber, who was awarded the Nobel Prize in Chemistry in 1983 for his pioneering studies. A particularly historic finding is summarized in the abstract of the seminal publication. When Co-NH3 5Cl++ is reduced by Cr++ in M, meaning 1M, hydrogen hypochlorite, 1Cl- appears attached to Cr for each Cr3, which is formed a Co3 reduced. When the reaction is carried on in a medium containing radioactive Cl, the mixing of the Cl- attached to Cr3 with that in solution is less than 0.5%. This experiment shows that transfer of Cl to the reducing agent from the oxidizing agent is direct. The paper and the excerpt above can be described with the following equation. Cobalt 1 chloride, NH3, 5, 2++, Cr, H2O, 6, 2+, Co, NH3, 5, H2O, 2++, CrCl, H2O, 5, 2+. The point of interest is that the chloride that was originally bonded to the cobalt, the oxidant, becomes bonded to chromium, which in its +3 oxidation state, forms kinetically inert bonds to its ligands. This observation implies the intermediacy of the bimetallic complex Co-NH3, 5, μCl, Cr, H2O, 5, 4+, wherein μCl indicates that the chloride bridges between the Cr and Co atoms, serving as a ligand for both. This chloride serves as a conduit for electron flow from Cr2 to Co3, forming Cr3 in Co2, the Kreutz-Tauber ion. In the preceding example, the occurrence of the chloride bridge is inferred from the product analysis. but it was not observed. One complex that serves as a model for the bridged intermediate is the Kreutz-Tauber complex. Quote, NH3, 5-Runc-4H4NIU. NH3, 5+. This species is named after Carol Kreutz, who prepared the ion during her PhD studies with Henry Tauber. The bridging ligand is the heterocycle pyrazine, 1,4C4H4N2. In the Kreutz-Tauber ion, the average oxidation state of Ru is 2.5+. Spectroscopic studies, however, show that the two Ru centers are equivalent, which indicates the ease with which the electron hole communicates between the two metals. The significance of the Kreutz-Tauber ion is its simplicity, which facilitates theoretical analysis, and its high symmetry, which ensures a high degree of delocalization. Many more complex mixed valence species are known both as molecules and polymeric materials. Mixed valence compounds. Mixed valence compounds contain an element which is present in more than one oxidation state. Well-known mixed valence compounds include the Kreutz-Tauber complex, Prussian blue and molybdenum blue. Many solids are mixed valency, including indium chalcogenides. Mixed valency is required for organic metals to exhibit electrical conductivity. As the extinction coefficient decreases, the coupling constant decreases, influencing the angle to increase. Mixed valence compounds are subdivided into three groups, according to the Robin-Day classification. Class 1, where the valences are trapped or localized on a single site, such as an antimony tetroxide. There are distinct sites with different specific valences in the complex that cannot easily interconvert. Class 2, which are intermediate in character. There is some localization of distinct valences, but there is a low activation energy for their interconversion. Some thermal activation is required to induce electron transfer from one site to another via the bridge. These species exhibit an intense intervalence charge transfer, IT or IVCT, band, a broad intense absorption in the IR visible part of the spectrum, and also exhibit magnetic exchange coupling at low temperatures. The degree of interaction between the metal sites can be estimated from the absorption profile of the IVCT band and the spacing between the sites. This type of complex is common when metals are in different ligand fields. For example, Prussian blue is an iron 2,3 cyanide complex in which there is an iron 2 atom surrounded by 6 carbon atoms of 6 cyanide ligands bridged to an iron 3 atom by their nitrogen ends. In the Turnbull's blue preparation, an iron 2 solution is mixed with an iron 3 cyanide C-linked complex. An electron transfer reaction occurs via the cyanide ligands to give iron 3 associated with an iron 2 cyanide complex. Class 3, wherein mixed valence is not distinguishable by spectroscopic methods as the valence is completely delocalized. The Kreutz-Tauber ion is an example of this class of complexes. These species also exhibit an IT band. Each site exhibits an intermediate oxidation state, which can be half-integer in value. This class is possible when the ligand environment is similar or identical for each of the two metal sites in the complex. The bridging ligand needs to be very good at electron transfer, be highly conjugated, and be easily reduced. Organic mixed valence compounds are also known. Examples are the oxidized form of tetrathiafulvalene and the radical cation of N-tetramethyl-p-phenylenediamine. See also inner sphere complex, outer sphere electron transfer.